Hello, my name is Ivan Konstantinov, and I am fourth-year computer game software development. This presentation is to demonstrate my final version of the artifact for my honors project. With the title, Can Artificial Intelligence Learn to Drive a Car Successfully Using Reinforcement Learning? The project's purpose is to showcase that artificial intelligence can learn how to drive a car independently. During the literature review, it was found that many different techniques for artificial intelligence were used in the past, such as deep learning, neural network evolution, deep reinforcement learning, and reinforcement learning. The advantages and disadvantages of reinforcement learning and neural network evolution were compared. It was found that reinforcement learning is exceptionally good at solving more complicated problems. The technique of reinforcement learning was not used many times before, and there were not many materials and experiments in this field. That's why I decided that the project will research reinforcement learning, because it can achieve sufficient results and further research is needed in the field to evaluate the algorithm. The programming languages used in the project are C# for the development of the environment and the game itself, because C# is the main language that Unity engine uses, and Python for the implementation of the algorithm for the artificial intelligence agent, as Python is the most popular language for artificial intelligence projects, and it is needed to start training using Unity ML agents. I started to develop a racing learning environment in which I can train agents using the reinforcement learning algorithm and proximal policy optimization technique to train and finish successfully the provided racetrack on their own. The learning environment was created on Unity engine, and the artificial intelligence agents were trained using the Unity ML agents asset. Many different agents on different tracks were trained during the project. Some of them could not even complete the first turn. Others want to complete the simple track with only left or right turns with a certain pattern, which was not the aim of the project training, and others could complete the whole track without colliding with a wall. The agents who were successful at finishing the track were further compared and evaluated. On this slide, three different tracks can be seen. The first picture is of the first track created for the project. This track was found to be inefficient, and it was changed to the training track in the second picture. The third picture is the evaluation track, which is the most complex track of them all. It was used to compare and evaluate the agents who managed to successfully complete the training track. The green polygon objects that can be seen are used as checkpoints to navigate the car agents to where they should go. The first video will show the agent from the most successful training, completing the familiar training track on which it has trained. In the video, we have a three-dimensional car model that can accelerate and brake. The car moves using the physics engine. The agent wheels move left and right all the time because they make many decisions in just a part of a second about where they should go and how to avoid hitting the wall. The walls around the track were designed to give a penalty and restart if the training of the agent hit them. There is a speed meter in the top left corner. This meter shows the speed of the car agents in kilometers per hour. During the training, there were many invisible checkpoints over the whole track that helped the agents to learn how to drive and gave them rewards. The agents received a small reward if they get through the right checkpoint and a large penalty if they hit a wall. This taught the agents successfully how to drive using the reinforcement learning algorithm. In the second video, the most successful agent who completed the training track is tested on the unfamiliar evaluation track. The evaluation took 4 different phases. In the first phase, the agents were warned to drive on a track with right turns only and small straight areas. It was found that this approach led to the agents warning how to do a circular motion rather than warning how to drive. In the second phase of the evaluation, the agents were tested on the same track but in a different direction, to check if they could manage to make left turns after they had warned to drive with right turns only. At this point, the experiment was so bad that the project took a different direction. And instead of training agents on the circular map, a more complex map with many left and many right turns and straight areas was developed. This was done in the third phase. The car agents succeeded in their training and warning. Multiple agents were trained simultaneously and the algorithm helped them to learn from each other. Many changes to the car agent's parameters and the wheels collider script and the car controller script were made also during the testing phase. Some of the agents trained could complete the whole track. So in the last phase of the evaluation, another complex track was created to check if the agents can manage to drive on a new track without any previous knowledge and training on this unknown track. It was found that only the 3 most successful brains produced during the training could complete the track. The best performance of an agent was recorded by the agent shown in the video. This agent successfully completed the training track and the evaluation track without colliding with a wall. Another conclusion is also that for the car artificial intelligence agent to train correctly, walls with triggers are needed, and if it hit these walls, it must be reset. The car agent does not need the start position to be random, and the maximum speed should be kept at 80 km per hour. Otherwise, it hits the wall colliders at above 80 km per hour. The agent could decide properly whether to move forward, backward, or stay in the same place after they had collected their observations. They gather their observation by shooting array in many directions. By doing that, they can find which object is a wall and which is a checkpoint. The agents were able to decide also if they are going to turn left, right, or stay facing in the forward direction. The conclusion is drawn based on the results of the successful pieces of training. The project has shown and proven that artificial intelligence can learn how to drive a car successfully in a racing environment using Unity ML agents with reinforcement learning and proximal policy optimization. The agents managed to complete perfectly the first complex track on which they were learning, and they also managed to complete the way more complex track which they had never seen in the training. This marks the end of my presentation. Thank you for listening.